Right, so we've looked at scatter plots, how to create them, how to come up with lines of best fit, whether it's your personal line of best fit or that created the actual line of best fit created by a computer. Now we're going to look at a little bit another way to analyze whether or not your line of best fit is appropriate for your data and your scatter plot. And we're going to get into a little bit later on about different types of fits, although not right this second. So residuals is what we're working on today. So you're going to be filling out your foldable. So the first flap says, what is a residual? And what a residual is the vertical distance from a data point that's on your scatter plot to the line of best fit. So if I have a scatter plot here, and I have a few points on my graph, and so here's my line of best fit that I'm sketching poorly. What the residual is the vertical distance. So you go to any one of your points, and I'm trying to draw this in, although it's pretty tight there. This is the residual. It's how far vertically it is from one of your points, or from each of your points actually, to the line. Now you have residuals that are positive and you have residuals that are negative. If your point was above the line, so in other words, your y value, think about the y value on this, like this point, the y value for that residual is higher than the y value on the line of best fit, so the point is actually above the line. Or sorry, the point is above the line, so that means the residual is going to be positive. Your y value is greater than the y value on the line. So you can almost think of it as the y value on the point as greater than the y value of the line. Now, if it's below the line, meaning your y value of the point is smaller than the y value of the line, then you're going to have a negative value for your residual. So you just have to remember that when you're calculating a residual, and it's just that distance. So we have two examples on your foldable that you're going to be answering. And so you have the residual for the point 4, 2. So line of best fit, we're going to look at, first thing, find your point 4, 2. So I'm just highlighting it here. The residual, and we're going to estimate it. We're going to assume these are at nice, clean points and that your line, we don't have the equation of the line, so we're going to assume that the line is cutting through those points nice and cleanly. But my residual would be this vertical distance. So I'm actually going to change to a different color here. It's this vertical distance from the point to the line. So the distance here from my point to my line is going to be just one space. Now, the thing I have to think about, though, is that my point is below the line. So when I say my residual here, my residual is actually going to be a -1. So point below the line. Point is below the line, so that's going to be a negative. Now for my second example here, the residual for the point 9, 8. So I'm going to find 9, 8. So 4, 5, 6, 7, 8, 9. And there is the point 9, 8. So residual, vertical distance, the point is from the line, the point is on the line, so the residual for that point would be just 0. So now we know what a residual is. Let's talk about what is the residual plot. So what am I going to do with these numbers, these residual numbers that I get from each of the points? I'm actually going to plot it because that plot is going to show me some other extra information. So the residual plot is a graph that shows the residuals on the vertical axis. So what you'll see is, and for residuals, we can have positive and negative numbers. So we want our x-axis to actually cut right through the middle. But these are your residuals on the y-axis. And then the independent variable, so whatever our x variable was, is going to go on the horizontal axis. So we're going to plot the residuals versus your independent variable, the one that's doing the causing, if you're thinking about a cause effect. Independent variables you covered in science class, but whatever your x variable is. So when we look at, and you can see on each of these plots it says RES up at the top, that's saying that those are the residuals. That's how you would show that your y-axis, this is a residual plot, and then you have your x variable on the horizontal axis. And notice The X values, we're only doing positives because in a scatter plot, if you're talking about data, a lot of times most of your data is going to be positive numbers, but your residuals have positives and negatives. So the different types of residuals you may see, if you have a strong linear fit, meaning, so this is not your scatter plot, these are a plot of the residuals. If you have your residuals that show, looking in this first pattern here, and you see these kind of characteristics, the distribution of the residuals, so how far apart they are on the x-axis, it's a random, so like up, down, and then it's also very tight, which means close to the x-axis. They're not really spread out, but they are random. Now, it might seem kind of confusing, but when we get into actually making some residual plots, it'll make some more sense. But a strong linear fit, meaning whatever my data look like, and I could translate this if I wanted to do it a little bit more carefully, but I have my line of best fit. I have a point that's a little bit above, I have a point that's a little bit below, a point that's a little bit below. If you look at the data, what it's saying is, and I'm not going to take the time to do it all perfectly, but if you're saying that your data is very, very close to the line, because notice the farthest away any of the data points is from the line is maybe this point, which is about 1.5. That's saying it's about 1.5 spaces from the actual line. You even have 2 points here that have a residual of 0. What does a residual of 0 mean? It means the points are actually on the line. Now, if you have a weaker linear fit, meaning the data is still linear, but not quite as strong, a little bit more spread out. So this would be more like R is about 0.9. Here, your correlation coefficient's more like 0.5, a little weaker fit. The distribution of the residuals is still random, but it's loose. It's further away from the x-axis. So they're definitely more spread out. So if you look at this, for instance, this residual shows that that point is 4 spaces away from the line. 4 spaces away from your best fit line. And we're not talking about your hand-drawn lines. We're talking about your computer-generated lines here. Now for the last example here, you notice that it goes in a very distinct pattern. Looks kind of like a parabola. Not quite a parabola, but close. A nonlinear fit, meaning your data looked, if I'm going to do a scatter plot here, your data looked maybe something like, and I'm just making an example here, it looks something like this, and you try to draw a single line. It means it's a nonlinear. It's not just data that can be described by just a straight line. Now that data doesn't necessarily match, so don't copy that. That doesn't match necessarily what the picture is. If we could go a little more carefully and get an idea of what the data looks like. But it's a nonlinear fit. So if the distribution of the residuals is not random, what that tells you is that another type of function, and we don't know a whole lot of types of functions at this point, but another type of function may be a better fit. So realizing that a line may not always perfectly fit our data. So the last piece here is we're actually going to do this example. So you have a best fit line and you're given the equation y equals 0.74x plus 1.4, and we're going to find out what the residuals are. This table is a good way to kind of keep yourself organized. We have x and y. These are the actual data points. So I'm going to go ahead and fill those in. First, I have the point 1, 2. I have the point 2, 3. I have for 3, x for 3, you can see you have 2 entries here. You have 3, 2, and you have 3, 5. You have 4, 4. You have 5, 6. You have 6, 5, and 7. You have 7, 7, 8, 6, and 8. And then I have 9, 8. So those are my actual data points. The predicted means what our line of best fit would tell us our y value would be. So how are we going to figure out when we make a prediction using our line of best fit? How do we figure out what that y value is going to be? Well, we plug in the values. So I'm going to plug in 1. I'm going to pause just to kind of save time in the video. I'd like you to pause and try and fill in. So we're just going to go ahead and fill in all of our predicted values. So for instance, the first one here, when I do 0.74 plus 1.4 should be 2.14. So pause, try and fill in the rest of this table, and then we'll come back and do the residuals. Okay, so double check your numbers, look down my list, and I definitely use the calculator, so don't be don't be afraid to use the calculator to do some of these. Okay, so we're going to do our residuals here. You've double checked your numbers. When we do the residuals, you can look at the line, you can see above and below and kind of do the distance. However, an easier way to do it might be to take the point, and we're only paying attention to the y value, and we're going to use kind of the formula here. You're going to take the y of the actual value minus the y that was predicted. If the actual point was above the line, when we take actual minus predicted, we'll end up with a positive number. If the actual point was below the line, then we'll end up with a negative number. So for instance, let's check the first point here. We have an actual value of 2 minus 2.14. So we should end up with, it's below the line, so we should end up with a negative number, and we do, negative 0.14. So I'm going to graph that. On my residual plot, I have x is 1 that I was using right here. X is 1, and I ended up with a residual of negative 0.14, which is really close to 0, but just below the x-axis. So again, actual minus predicted. Careful with the decimals here. This is 0.12. So at 2, I'm going to be at 0.12, and you can see that point was just slightly above the line. So I'm going to kind of circle as I go along to kind of match things up. So actual minus minus predicted, minus 3.62. That would be negative 1.62. So at 3, yep, 3 is my x. I'm going to be at negative 1.62 for my residual. So a little bit below negative 1.5. So I was doing this point. And now I'm going to do the point above. So actual minus predicted. And that's going to be 1.38. So at 3, I'm going to have 2 points. 1.38. For 4, I expected 4. I got 4.36. So that's negative 0.36. So at 4, I'm at negative 3.6. And that was this point. Oops, sorry. That was this point, just below the line. For 5, my actual was 6. My predicted was 5.1. So that's 0.9. Almost 1. Actual minus predicted. That's negative 0.84. So at 6, I'm at negative 0.84. That's this point and this point. Actual minus predicted. That's 1.16. Yep, positive 1.16. So I have another point. Just keep track of what x's you're doing. Those were both 6. So that was that point. At 7, I actually had 7. I was expecting 6.58. So that's 0.42. It's a little under halfway, just above the line. Actual minus predicted for 8. And I have 2 values at 8 here. So this is going to be negative 1.32. So at 8, that was below the line. Actual minus predicted, that's 0.68. Yeah, 0.68, so a little more than halfway. That was this point. And then the last point, I'm going to double check that number. Oh, my problem is that on my actual point, I didn't count correctly. So it's at 8. So it like the one we did, it looks really, really close to the line, but when we look at the predicted number, so we do 8 minus 8.06, we actually get negative 0.06, which is so close to 0 that we really can't graph it much below 0. So there's our residual plot. And what do we notice about our residual plot? We notice that it's randomly scattered, and pretty closely gathered towards the x-axis. It's hard to say whether it's closely